because we're working with image, and image is a very special data type that carries different properties of the data and also specific operations on the image data. And DPC++ supports a dedicated image object. Image objects are special data type for image operations. And these image objects differ from buffer objects in several ways. First, it's an opaque data type that cannot be viewed directly through pointers in a device code. So the actual organization of the values in this image objects are hidden from the programmer. And the image objects are multidimensional, so itself has multiple dimensions in data structures, and they are limited to a range of types relevant to graph operations. And they are not designed to be using freely to implement arbitrary structures. And they are dedicated for image data types. The image objects exist to offer access to special function hardware, which are available on graphics processors that are designed to support highly efficient access to image data. Filtering operations enable efficient transformations of image data based on collections of pixels. To give you an example how we may operate on image data, we show here a Z-order mapping. Z-order mapping is to map multi-dimensional data to one dimension in memory. For example, we can store texture maps for restoration in Z-order. As we show on the diagram on the right, we have original image. We have the rows and columns, but instead of storing these row of values in sequence, we go through a Z type of pattern. So we store this pixel and then this pixel, and then go to the next row, store this one, then back to the first row, to this one, and then this one, and then this one, and so on. And then we jump from the second row to the third row to store this pixel and then this pixel, and so on. By doing this, we can increase the spatial locality of reference during texture mapped rasterization. This can help cache lines to represent rectangular tiles, and increasing the probability that nearby access are already in the cache. And it decreases the probability of costly page breaks in SDRAM or DRAM or DDRM. This kind of organization is important because image operations can involve many arbitrary transformations, rotations, and scaling. Using this kind of specialized mapping will help us to improve locality and improve performance. So as you can imagine, image objects can be utilized to facilitate this kind of mapping. To use image objects for image convolution example, we'll first create image objects for input and output data. That is the source image and destination image. That is the input image and output images. So the way we create image objects is to use image, the object type, and then we specify what's the dimension of the image. It could be 3D, could be 2D. In our case, we have a 2D image. And then the name of the image object. We use this image object is going to be defined by several arguments. First is the host pointer, and then followed by the channel order and channel type, and then the size of the image. The first argument, image in, is a host side buffer of certain size, which typically the image column by image rows. And each data in this buffer is of floating point type, or float, and that represents a pixel value in the original image. And in the example image, we provide a cat.bmp. Each pixel is of a 8-bit color, so we just use R as the channel order because it's really not it's a gray image. It's a gray color image. We only use one channel, so all the other channels will be replicated using the same value if we specify R here. And the channel type is set as floating point, so FP32. And finally, the last argument is the size of the image. And we have a 2-dimensional range, and that specifies the column and the rows of the image. Next thing we have to do is to create an accessor to access the image. Similar to accessors to buffers, we need to create this accessor to image with access permissions. It could be read and write, or both read and write. The accessor is a way to access the memory in the image. This is an example. We have an accessor, and we use float 4 to represent the 4 channels for the pixels. It's 2D, so we're using a 2-dimensional image, and we are doing read mode as this is the input image, so we only read the pixels. The target is an image object. The accessor's name is a source pointer, and we use the image object we just declared as the image, and then followed by the handler of the lambda function. The accessor element type is used to specify how the image should be read from or written to. So with this accessor, we can define the ways to access this image data. The type of data could be floating point, that like we use with our example. It could also be integer 4, unsigned integer 4, etc. For other ways to encode the pixels. For accessing the image, we need another object which is named sampler. Samplers are used to specify the way in which the coordinates map to a particular pixel in the image. So with samplers, we do not have to manually select the rows and the columns while we go through the pixels in the image. Sampler can help to simplify that process. In our example, we use this sampler by saying that we are not going to normalize the coordinates, so it's unnormalized, which means that we're going to use the row number and column number rather than a normalized value to locate the pixels. And with the sampler, we can specify how we should do. With the sampler, we can specify how we should do when we found a pixel that's falling on or beyond the boundary. By doing this accessing mode clamp, we're saying that any access to outside the image bounds should clamp to the edge of the image. Also, we set the filtering mode to be the nearest. That is to say that any floating point coordinates, by calculation, we're going to use the nearest pixel data rather than applying a linear filter. So with this image object and the associated data types for sampler and with associated image-related data types, we can re-implement this image convolution kernel. So assume that we already declared the image object, the accessor, and the sampler as we did in the previous slides. Well, first, so in the kernel function, in the kernel lambda function, we first declare sum, which is a vector of 4 floating point numbers, because we have 4 channels to represent a pixel. And then we will iterate through the filter rows, and we will iterate through left and right and up and down. But one thing you can notice here is we don't have iteration through the one thing you can notice here is we're going to use coordinates to one thing you notice here, we use coordinates to record. One thing we notice here is we use coordinates, this 2-element array, to specify the locations or coordinates of the pixel. This row is the pixel that this work item is going to work on, and that add with this iteration, add with this loop iteration I will give us the locations surrounding that pixel in a horizontal axis. And then likewise we have another dimension, and the locations of the pixel in the original image is specified using the column and this other loop iteration variable j. And we can then use a image specific function read. With this image object, with this accessor to the image object, we can read the values from a pixel. The read function takes 2 arguments: the coordinates, which specifies the rows and column, and then the sampler object. The sampler object specifies how we're going to deal with the boundary pixels, or any pixel that beyond the boundary, and also whether we use normalized or unnormalized coordinates. So that's already specified in here. So as you can see, when we use this image object specific read function, we do not have to check for boundaries because that's already handled by the image object. And that's exactly the advantage of using that here. And the next, so this read function will return a vector of 4 floating point, and this pixel represents the values of the 4 channels. And then we can use the filter value in corresponding location to multiply with the first channel out of this 4, out of this 4 value vector, out of this 4 element vector, because in fact all the 4 channels have the same value, and then we accumulate the product to the first element of this vector. So once the filter is applied to the pixel and its surrounding pixels, we can then write the new pixel value back to the image. So we'll use this column and row which we had used to specify the current pixel in the original image, and we put that into the coordinates, and then likewise we use a write function specific to this accessor to the image object. We will write the value sum to the corresponding location. So this will, the new pixel will be put into the output image. So that's a a different implementation of the image convolution using image objects. Next, we'll see a demo of image convolution example on Intel Dev Cloud.